G'day viewers. In this episode we're going to look at Barry Castillio's contribution to the Bob Lazar story. Castillo was Lazar's colleague at S4 and next to no information exists about him, nor has Lazar spoken about him in anything more than a passing comment. So this seems to imply that Castillo's contribution is negligible, doesn't it? Well, no actually. In fact, we'll show you how Castillo's contribution has been critical and indeed drives much of the technical content you'll encounter on the internet regarding the Lazar story. We're going to show you that based upon the presumption that Castillo constructed a model of the space alien element 115 reactor at S4, as reported by Potter, the information supplied by Lazar and propagated across the internet introduces a scaling problem. In other words, some of the technical specifications supplied by Lazar doesn't align with the mass density of element 115 predicted by standard nuclear physics theory. This doesn't mean that Lazar has lied at any point. It means that he hasn't told his story clearly enough. Considering how fed up Lazar seems to be about this whole S4 phenomenon, I'm not surprised. Firstly, I need to preface what comes next by the fact that Lazar didn't know what the gravity A wave fundamental wavelength was because he didn't derive it from particle physics like we have. Moreover, he didn't derive it from particle physics because he hasn't unified general relativity with the quantum vacuum like we have. Not being able to do this prevents anyone from deeply understanding how everything hangs together. Okay, now that I've defended Lazar's failings, I'll explain why Castillo has played a very significant role in the Lazar story. If you watch this presentation to the end, you'll see that Castillo constructed a half-scale model of the element 115 reactor. This is a standard and normal engineering practice when scaling systems, designing prototypes, or reverse engineering. It is based upon a standard engineering technique termed Buckingham Pi theory, published by Edgar Buckingham in 1914. The technique has been applied to more areas of science than I could possibly mention here. It has been very widely utilised for a very long time. Bob Lazar may have stuck his head into the sports model and had a look around, but he physically worked with a half-scale mock-up of the element 115 reactor built by Barry Castillio. Thus, much of the technical information regarding the element 115 fuel and reactor stated by Lazar has come from the half-scale model built by Castillo, not directly from the full-scale sports model. When this scaling factor is fed into the relevant scientific equations, everything lines up and the element 115 mass density problem disappears. So, Lazar is truthful in his technical recantation of his time at S4, but it has seemingly never occurred to Lazar to emphasise the fact that he mostly experimented with a half-scale model, not the full-scale sports model sitting in the hangar. I suppose he might not have realised to emphasise this because for any scale model it must always utilise element 115. It cannot be substituted, and as far as Lazar is concerned, the scientific miracle lives in the element 115, not in the engineering system as a whole. Building a scale model and experimenting with it rather than running berserk and potentially breaking the full-scale sports model is entirely logical when you pause to think about how irreplaceable the sports model actually is. In other words, you don't give your kids an expensive first car. Therefore, as Lazar reports his observations, listeners are unaware that they apply to a half-scale model. Most people listening to Lazar tell his story might assume that it applies verbatim to the full-scale sports model, but the scientific reality is that it doesn't. Bottom line, Barry Castillio has had an enormous impact on the Lazar story and most people are unaware of it. Anyway, that's enough rambling from me. Let's get into it. Let's start by looking at the element 115 reactor as described by Ken Wright, and presumably built by Ken Wright. What we're interested in are the physical dimensions of the model and what that means for the mass density of element 115. Since Ken Wright doesn't provide exact dimensions to his model, by necessity we are required to eyeball the situation and execute some guesstimates. Ken asserts that the pellets, that is the element 115 fuel disks, were about the size of a 50-cent piece and weighed about 223 grams. Unfortunately, this statement is a little ambiguous. We can interpret it to mean that each element 115 fuel disk weighs 223 grams, or we can interpret it to mean that the resulting element 115 fuel wedge weighs 223 grams. So, can we determine which one he means? Yes is the short answer. We show on page 73 in the link appearing at the bottom of the screen that if we interpret 223 grams to represent the mass of each element 115 disk, the associated mass density is implausible because it violates standard theory quite substantially. Thus, we can only interpret the 223 gram value as referring to the mass of the element 115 fuel wedge. Importantly, Ken Wright uses the word about to describe the mass of the fuel wedge, but Bob Lazar states its mass with less doubt in various interviews. Once again, we are confronted with ambiguity because the use of the word about could mean somewhere between 222 and 224 grams, or something else entirely. However, going forward, we will assume that the mass of the element 115 fuel wedge has an exact value of 223 grams. Regarding the diameter of each element 115 fuel disk, Ken Wright is once again ambiguous by describing its size as about the same as a 50-cent piece. We must assume that he means a US 50-cent piece. Hence, the base length of the fuel wedge must also be about the diameter of a US 50-cent piece. Moreover, by eyeballing Ken's model, we can estimate the height of the fuel wedge to be approximately 2 to 3 times the base length. In addition, Ken Wright states that the geometry of the fuel wedge constitutes an isosceles triangle. Anyway, when we run the numbers on page 22 to 23 in the link appearing at the bottom of the screen, we find that the mass of the fuel wedge in the model shown is well below the 223 gram requirement. From this, we're able to conclude that the Ken Wright model is constructed between 1/3 scale to 1/2 scale in order to preserve the Burkhardt-Frick mass density value for element 115 of 13.5 grams per centimetre cubed. In other words, standard nuclear theory says that the Ken Wright model is definitely not a 1-to-1 scale model. Let's now look at alternative dimensional interpretations of the fuel wedge. In this frame, we see 3 pictorial interpretations of the element 115 fuel wedge. One illustration originates from Paul Edwin Potter in 2008. The other 2 originate from Seton Ball in 1998. Although these illustrations are separated by 10 years, we have no way of knowing if they are truly independent or if Potter copied Ball. However, for the purposes of this exercise, we shall assume that they are independently formulated. Unfortunately, neither Potter nor Ball includes dimensional information on their illustrations. This is a seriously limiting obstacle, so we are compelled to overcome it. However, the best we can hope to achieve is a reasonable guesstimate. To facilitate our guesstimate, we have introduced purple dimensioning lines. Once this is complete, we can project the height and base length of the fuel wedges via the red lines appearing on screen. The first thing we'll do is measure the length of the vertical red line, then the red hypotenuse line. With this information, we can guesstimate the height to base length ratio of the Potter and Ball illustrations. And lastly, we can measure the hypotenuse length of illustration number 1, which Ball claims is drawn to scale. 2 very important pieces of information have been obtained via our analysis. Firstly, the height to base length ratio of Lazar's element 115 fuel wedge is approximately equal to 2. And secondly, the guesstimated base length of the element 115 fuel wedge is almost exactly equal to the gravity A wave fundamental wavelength we have derived in previous episodes. This is no small achievement because, don't forget, our gravity A wave fundamental wavelength was derived from particle physics, that is, the element 115 nucleus, not from the illustrations appearing on screen. Let's now do a side-by-side comparison of what these illustrations are saying compared to what we have derived in the previous episodes contained in our Bob Lazar playlist. In this frame, we have taken the Potter illustration and roughly proportioned it in accordance with our element 115 fuel wedge manufacturing process diagram. Please remember that from the previous slide, we have determined that the Potter and Ball illustrations are identical, so it doesn't matter which one we utilise now. It's simply a matter of convenience. Hence, for the moment, the Potter illustration is preferable. What's important to recognise here is that the height to base length ratio is 2 for both diagrams. However, the base length of the Potter fuel wedge is half the base length of the Storti solution appearing on the right hand side. In other words, the Potter and Ball solutions depict a primary fuel wedge with a base length of 1r and the Storti solution depicts a base length of 2r. So the obvious question becomes, who is correct? Okay, let's do a deep dive into it. In this table, you'll see a column labelled number of discs. This denotes the number of element 115 fuel discs required to manufacture a cone and consequently a primary fuel wedge. For conceptual demonstration purposes, we have held the required mass constant at 223 grams. This means that the calculated mass density varies with the number of discs, as shown in the table. If you find this demonstrational concept confusing, just focus on the 14 disc solution. For this reason, we have bolded the number 14 in red. You'll also see 6 columns of calculated data, displaying implausible, plausible and implied results. Please pause the video and take a few moments to study the table. When we analyse the Potter and Bale geometric representations of the primary fuel wedge in the context of the calculated data, we run into problems. We can clearly see that the Potter and Bale base length, that is, when the base radius is equal to 1/2 r, the required mass density far exceeds Burkhardt-Frick's theoretical guesstimate of 13.5 grams per centimetre cubed, as well as our calculated guesstimate of 13.7 grams per centimetre cubed. Hence, the Potter and Bale base length value of 1r may be discarded. In other words, their graphical illustration of the primary fuel wedge is not presented at a 1-to-1 geometric scale. In fact, we can confidently claim that it has been sketched to 1/2 scale. Thus, Bale's claim of actual final size, which we saw previously, may be true, but it, as a solution, doesn't align with mass density expectations. Therefore, Bale's claim of actual final size is not what we'll find under the hood of Lazar's sports model. So, is there some kind of middle ground where Lazar, Wright, Potter and Bale can all be satisfied? Let's have a look. When we assemble what we've discussed so far, we can generalise with certainty that the height to base length ratio of the primary element 115 fuel wedge is somewhere between 2 and 3. For the purpose of this exercise, we shall sit in the middle and assume a value of 2.5. The next thing we'll do is constrain our analysis by Ken Wright's claim that the base length of the element 115 primary fuel wedge is the diameter of a US 50-cent piece. Although Ken Wright clearly states that this dimension is only an approximation, we shall assume that it is an exact solution in order to press forward. When we apply these constraints to a primary fuel wedge with a mass of 223 grams, we compute an atomic number of 246. I should mention that our computational algorithm utilises standard nuclear physics theory as a baseline reference. That is, a stable isotope of element 115 exists with an atomic weight of 299. This means that the primary fuel wedge isn't composed of element 115, it's actually composed of element 246 instead. However, it's interesting to recall the Bob Lazar claim that another island of stability exists around element 247, so our results seem to support the possibility of a second island of stability existing around element 247, just as Bob Lazar claims. As you can see, we have named element 246 Fed income. We have moscovium on the periodic table. We have livermorium on the periodic table, so why not Fed income on the periodic table? If you're an Australian watching this, you might be chuckling about now. So, are we saying that Bob Lazar really worked with element 246 instead of element 115? No, we are not saying this. The content of this slide is an interesting bit of fun which explains the obvious and apparent scaling problem we have already discussed. However, it is reasonable to assume that someone at some point would have tested the alleged space alien material to determine which element it actually was. So then, what do we think is the likely explanation for the so-called scaling problem? Paul Edwin Potter states on page 365 in his book titled Gravitational Manipulation of Domed Craft that an element 115 reactor had been built by Bob Lazar's S4 associate, Barry Castillio, which had been built prior to Lazar's arrival at S4. The first rule of physical modelling that any mechanical engineering student will tell you is that mock-ups are almost never constructed on a 1-to-1 scale. This is precisely why students are forced to study Buckingham Pi theory. It's a physical modelling scaling technique published by Edgar Buckingham in 1914. It allows people to execute research, design prototypes and reverse engineer at a convenient and cheaper scale of reality. This is standard engineering. It is well established, well understood, and extensively practiced. So then, if Barry Castillio executed standard engineering practice when he built the Element 115 reactor mock-up, he would have built it to some sort of convenient scale, less than unity. If the actual diameter of the Space Alien Element 115 reactor dome has been correctly reported by Potter to be 280mm, then it is almost certain that Castillo would have constructed the mock-up to 1/2 scale. To understand why he would have chosen a 1/2 scale is easy. It only requires 1/4 as much Element 115 material. That is, when we approximate the shape of the primary fuel wedge to a triangular prism. Given the priceless nature of Element 115 material, building a 1/2 scale mock-up is easily understood. Therefore, the Element 115 reactor Bob Lazar played with was a 1/2 scale mock-up. Lazar reported the associated dimensions when he left S4, and sources on the internet continued to report Lazar's dimensions like a parrot, without a rigorous analysis similar to what we have executed in our Bob Lazar playlist. The reality is that the information provided by Bob Lazar doesn't align with the theoretical mass density of Element 115 unless the mock-up is constructed to 1/2 scale. By following standard engineering practice and building mock-ups to 1/2 scale, the US government effectively quadrupled its working stockpile of Element 115 material. I will close this presentation by stating that it would not have been difficult for Los Alamos National Laboratory to smelt and recast a certain quantity of Element 115 fuel disks supplied by the space aliens into a batch of smaller diameter disks, that is, from a full-scale radius of 2R to a 1/2 scale mock-up radius of R as appears on screen. The thickness of each disk must remain constant at 1/4 R across all mock-up scales. If this disk thickness is not preserved, then the cone and wedge manufacturing instructions will need to be somewhat modified.